reionize the universe. Yes. I mean, it's not getting finished till 12. Like, there is no way. Yes, thank you. Okay, so hi everyone, welcome back. Okay, so over coffee, I'm sure you had ample opportunities to think how to solve this problem, which is a key problem in our field now. So, okay, so come on, give me solutions. So, if we take the star formation rate density that we are inferring from the James Webb at face value, we have too many photons for reionization. So you would reionize too early, giving you a very high optical depth. So what's the solution? Sorry, who said feedback? Very good. Okay, so we're getting there, super advanced, but yes, a solution. Okay, what else?
What about the recombination?
Okay, another answer, very good. Yes, okay.
Could it be extremely homogeneous reionization?
Okay, sure. Okay, sorry, I saw more hands up, but just shout out your answers. I mean, you don't have to wait for opportunities. Yes?
Actually, I was confused if these ionization fractions that have been calculated, are those already taking into account an assumed escape fraction? Like, are these all ionizing photons that are escaping? Or are these ionizing photons that are being formed by these star forming regions?
Yeah, so far we assumed an escape fraction of 1, right?
Okay.
Yeah. Is this a solution? Can you just scale the escape fraction? For everybody who is unconvinced. Okay, so let me remind you guys of the equation that we were working with. We were saying that the time evolution of these ionized regions, I'm just going to do proportional, is proportional to production rate of ionizing photons times the escape fraction minus some sort of recombination timescale, which depends on the number density of hydrogen atoms and some kind of clumping parameter, which we are going to talk about. Okay, so here what we are doing is we are assuming an escape fraction of basically 1. So what do you guys think? Can all the photons that you produce within a galaxy, are they going to emerge out of the galactic environment into the IGM? Very good. So this is a very, very basic solution, which you can say, okay, so I am producing a huge amount of ionizing photons. So again, let me just focus on this evolving initial mass function model where you have the largest number of ionizing photons produced. So here now I'm showing you the total number of ionizing photons produced per co-moving volume. So production rate density of ionizing photons as a function of redshift. So here now this goes out to a redshift of 20. The yellow line is how many photons you would intrinsically produce if you take the star formation rate density that you are measuring at face value. Now you can play a really simple game. You can say, well, okay, how many photons should escape out for me to be able to match all of these reionization observables? So the electron scattering optical depth and the history of reionization. And you find something like 6% of ionizing photons should escape. And this is just a fudge factor at this point because this is independent of mass. It's independent of redshift. You're just scaling the total number of ionizing photons by some escape fraction. So if you do this, it brings the total number of ionizing photons that are now emerging into the IGM. It reduces this to the yellow line, which you can see is matching all of the observables that we have. So those are the data points that you see. This is something that has also come out of observations. So here I'm showing you some of these extremely deep observations. So we were discussing about James Webb looking at lensed fields. So you can really look at low luminosity objects, which are magnified because of lensing. So here, again, number density of ionizing photons as a function now of the UV magnitude. This is from a survey which is called UNCOVER. And they are detecting galaxies out to UV magnitudes of -15 at a redshift of 7. So these are basically equivalent to looking at dwarf galaxies of the Milky Way in the local universe. But we're looking at them at a redshift of 7. So this is really the deepest we have ever gone. And what they are showing is that for escape fractions as low as 5%, In principle, we have detected enough galaxies that can provide enough ionizing photons to reionize the universe. So you would say, okay, but it seems there's no overproduction crisis. Reionization is going as per plan. But let's have a think about what this escape fraction actually means. So what we are demanding is that we have star formation, which produces a lot of ionizing photons. Could be star formation, could be black hole accretion. At this point, we don't really care about the sources. These ionizing photons are going to get absorbed, not scattered, but absorbed both by neutral hydrogen and dust within the ISM of the galaxy. So for example, along this line of sight, maybe the escape fraction will be negligible. Let's say it's more or less 0. If you are able to create channels because of, for example, supernova feedback or maybe AGN feedback, you could create these channels through which ionizing radiation can escape out of the galaxy. So now, the first thing that you will notice is that this is a line of sight dependent quantity. So observationally, you're looking at a given line of sight, and maybe you measure some amount of escape, and you would call that thing a Lyman continuum leaker because it has Lyman continuum photons. Along another line of sight, you would see maybe 0 ionizing photons escaping out, and so you would say this thing is not leaking Lyman continuum photons. The problem is that this is really along the line of sight observationally. Along another line of sight, something could be leaking 100% of its photons, so you don't know. Theoretically, this has been also extremely, extremely hard to model, and I think Laura is going to tell you more about this, because this really depends on the structure and the turbulence within your ISM. So where are your star-forming or black hole accretion regions? How is your gas and dust distributed as compared to the regions where you are generating your ionizing photons? How many channels can you create because of your supernovae or because of black hole accretion, which really depend upon your assumed initial mass function, your star formation rate, your supernova rate. And another problem is, theoretically, we are in a better situation because we can actually look at different lines of sight, and we can say what is the average escape fraction from a galaxy. So this is what people are trying to do theoretically. The key problem is that this really depends on how far from the galaxy you look. So this has been a key point of contention in simulation. So if I look at half of the virial radius, which you would say is still kind of the circumgalactic medium, versus if I look at 2 times of the virial radius, the average or the angle averaged escape fraction that you infer is very different. So this is why it's an extremely ill-defined quantity, because we're basically using it as a parameter to just scale the emerging number density of ionizing radiation. And if you would put all the data that we had pre-James Webb, there wasn't any specific trend that we were inferring with almost anything. So here, for example, is the escape fraction as a function of redshift. These are all observed points. So these are all observations for things which are Lyman continuum leakers. A given color shows you the values from a given group, who are trying to reduce the data in the same way, probably at the same redshift. What I want you to notice is these 2 points, just to give you an example of the complexity of the process. So here, at a redshift of 3.5, where your Lyman continuum photons are not completely absorbed by the IGM, you can still see them. For this source, you are inferring an escape fraction which is much less than 10%. So the upper limit is of the order of 10%. From the same group, at a redshift of about 2.5-ish or 3-ish, they find another source where the escape fraction now is approaching 100%. Now, you don't know if this is because of the line of sight along which you're looking. So maybe by whatever reason, you are just hitting one of these empty channels through which you can have a lot of escape of ionizing radiation. Maybe this is driven by AGN, which are able to drive out huge outflows, create empty channels. Maybe it's a spatial segregation between where you're producing the photons and where your dust is sitting. You don't know. So this has been a really challenging problem to address for reionization, because both theoretically and observationally, it seems like there's no solution from first principles. So can I, well, okay, so maybe let me not ask you questions because we don't have time. So I think one of the key problems observationally was that if you are at very high redshifts, imagine these ionizing photons come out of the galaxy. They're immediately going to encounter neutral hydrogen. So they are going to get absorbed by this neutral hydrogen that is sitting around the source. So from extremely high redshifts, you can't directly detect them at all. So at redshifts above 4, it's very hard to do direct detections of these Lyman continuum photons, which are escaping out of galaxies. Even when they are detectable, generally you have extremely low signal-to-noise ratios, which makes it very hard you kind of get an upper limit on how many of these photons could be escaping, but that is basically it. In terms of physics, as we have been discussing, in terms of modeling, this has been an extremely hard problem to model because how does neutral gas, the sources are co-spatially located with respect to each other, how much turbulence you have in the ISM, how much dust you have, what is happening along a given line of sight. All of these are going to determine the escape fraction along a given line of sight. Another thing that might be of interest and that has started to emerge is that if I need to create an empty channel, it's not going to happen instantaneously. Supernovae start exploding 3 million years after star formation. They will need a certain amount of time to push out gas and clear this channel so that Lyman continuum photons can escape. But by the time this channel opens, if you guys remember, we said that the production rate of ionizing photons drops off really steeply with time. So if this is the production rate as a function of time, the slope is minus 3.9. So within about 10 million years, most of your ionizing photon production is gone because this is mostly driven by young massive stars. So imagine it takes 10 million years to open a channel, but by this time, you're not producing too many ionizing photons anymore. And so there is also a timescale problem when you try to model this physically. How long do you actually have between the production of ionizing photons and the creation of empty channels? So this has remained extremely, extremely hard to do from first principles. But I think Laura will also talk to you about this, so I will just do this very briefly. So people have started doing this experiment to look at the escape fraction correlation with galaxy properties at very low redshifts. So this is called the low redshift Lyman continuum survey, which is at a redshift of 0.3. So super low redshift. And we're trying to find correlations between the escape fraction and galaxy properties. And the hope is, if you can correlate them to some fundamental property of the galaxy, maybe you can extrapolate these relations to high redshift. So one of the most crucial relations that has emerged is to do with what is called the UV spectral slope, and you guys will hear a lot more about this later. The UV spectral slope basically tells you the flux as a function of wavelength, and this is roughly between 1500 and 3500 angstrom. So you are looking at this part of the spectrum. You try to fit it with a slope, and this is the beta slope or the UV spectral slope. The bluer the slope is, the more is the contribution from young stars. And it means that there's not too much dust or metals in the vicinity of these sources. As you increase the fraction of dust and metals, the slope will become more and more red. So you don't have to remember all of this. All I want you to remember is that the steeper the slope, the more metal-free or dust-free the stellar population. And this is really crucial because one of the most important correlations that have emerged is that the escape fraction actually correlates extremely well with this beta slope or the UV spectral slope. So if you look at objects which have very blue slopes, so which are very young, dust-free, metal-free, the escape fraction is actually quite high. And the escape fraction decreases as the beta slope becomes redder, which means that your stellar populations are becoming older and you have increasing amounts of dust and metals. And now this is useful, right? Because we can track stellar populations in early galaxies. We can even try and see how much dust and metals they have. So this is one of the most fundamental correlations that has emerged. And this is something that we are actually going to apply to our galaxies at high redshifts. And I will just show you what happens when we do that. Yes?
This is for stuff in galaxies. Is there the same correlation for
We don't have enough samples. And quasars are also hard to disentangle because when you look at the spectrum, it's the spectrum from both star formation plus the accreting black hole. So that has remained extremely, extremely hard. I'm going to show you, you can do like a guessing game to calculate the escape fraction from black holes. Yes. Okay, so the next thing that I wanted to discuss with you all is to figure out, so far we have been basically working with star-forming galaxies. So the question now is which kind of star-forming galaxies should actually contribute the most to reionization? Should it be the most massive galaxies? Should it be intermediate star-forming galaxies or really low-mass galaxies?
It depends on the relation between mass, so luminosity, and escape fraction.
Oof, okay. Okay, can I start with really zeroth order? Okay, so let me start with the halo mass function. So number of halos per co-moving megaparsec as a function of halo mass. This is what the halo mass function looks like. So let me say this is 10 to the 7 solar masses, 10 to the 12 solar masses. So you have a steep slope, right? You have a lot of low mass halos. And beyond a certain mass, beyond what we call the knee mass, this will fall off exponentially. So now what can you do to see which of these? So what is the first thing you need to do? Sorry?
Check the abundance. I mean, there's more low mass stars in the galaxy, which means they would be able to contribute more consistently than low mass.
Very good. Okay, so what is the first quantity you need in order to calculate how many ionizing photons you're going to produce? NUV. Sorry? Okay, NUV. What is NUV an indicator of? Star formation. Okay, good. So the first thing you need to do is to link the star formation rate to any of these halos, right? So now what happens to star formation? Can all galaxies support the same amount of star formation? And I see people shaking their heads because what happens to low mass systems? Okay. Go for another word instead of quench because that is like an evolutionary thing. Sorry? Okay, I was looking for feedback, but okay, I will take it. Okay, so the star formation efficiency is actually going to, in general, increase. So this is your star formation efficiency. It will increase as a function of halo mass. Can you all agree with this? Because for low mass systems, you will have a lot of supernova feedback. So what you can do is you can try to calculate what is the maximum star formation efficiency any galaxy can support. And this is really easy because you equate the total energy you get from the supernova to the binding energy of the halo. Okay, so let me open this up. So if I have a halo, what I'm demanding is the maximum star formation efficiency that you can support is that for which the supernova energy equates the binding energy. What is the expression for the supernova energy? Okay, this is a hard one. I would just do it by myself. Okay, so let's say a fraction F of the total supernova energy couples to the gas because it will not be 100%. How many supernovae you have depends on the initial mass function. So this is the supernova rate. And each supernova, let's assume, produces 10 to the 51 ergs of energy. Equate this to the binding energy of the halo. So imagine I have a gas mass that I start with minus some star formation efficiency to form stars. And then this is the circular velocity of the halo. Sorry, is this making sense? If it's not, then please tell me. You can even get rid of this term if you assume all of the supernova energy is just going to basically couple to the gas energy. So this is how many supernovae you have per unit of stellar mass formed. So this depends really on your initial mass function. For a saltpeter inertial mass function between 1 and 100 solar masses, this is 1 over 134. So 1 supernova per 134 unit of stellar mass formed. This E51, so this guy is the total star formation efficiency that you can support, mg E51. And what I want you to just see is that basically this only depends. This is a constant, this is known. So the star formation efficiency basically just depends on the circular velocity of the halo. So this is literally proportional in some sense to the total halo mass that you have. This is why we can assume that the star formation efficiency increases as a function of the halo mass. Yes?
Sorry, it's a little hard to see. Can you just, on the line before E supernova, or you equate the energies, the line below that, what each thing is again?
Oh, sorry. So this is the supernova rate,
Okay.
stellar mass. Sorry, where is the light? No, it's okay. I can do it if you just tell me where it is. Okay, there we go. And then you can switch it off in 1 second. Sorry, but it's I realize it's not very easy to see. Like, can you guys see it now or yes? Sorry? Oh yeah, of course. Yes, okay, I can be in a corner. Okay, so basically what we are trying to do is to see that the star formation efficiency is basically just going to scale with your halo mass to some power. So now we are in a situation where low mass galaxies are not very efficient at producing stars. There's many of them, but they are not super efficient at producing stars, basically because a small amount of star formation will produce enough supernovae to get rid of the rest of the gas. High mass galaxies are super efficient at star formation, but there's not too many of them. And so what is going to win in terms of how many ionizing photons you can actually produce? I hear whispers. It's okay. I mean, nobody really knows the answer, so please feel free to speak up. Sorry? Okay, but you know, like basically what is going to happen is if you look at so I can change this halo mass. Let me replace this by the star formation rate. For low mass galaxies, the star formation rate will be really low. So there's many of them, but they are not forming too many stars. High mass galaxies are going to form a lot of stars, not so many of them. So in general, it's this intermediate mass stuff which is going to win in terms of they will have a lot of star formation and there's enough of them. So you guys can go do this really a simple calculation by yourself. It's all a game of how many stars you can actually form. So what is the star formation efficiency that you are imposing? And what is the escape fraction that you are imposing? Because there is a secondary problem to this. So we are now in this situation where we are saying that the star formation rate is proportional to halo mass to some power alpha. But the escape fraction is, in general, inversely proportional to the halo mass to some power beta. Because when you have low mass galaxies, they will have a lot of young stars, low amounts of metal, low amounts of dust, so the escape fractions will be higher. And so it's all a balancing game of how many ionizing photons can you produce versus how many of them can actually come out of the galaxy. So this is what I was trying to show you guys here. So this is a really simple analytic calculation you can do. Start from your halo mass function, assume a cosmological ratio of baryons to dark matter. Try to calculate the star formation efficiency, at which point the supernova energy equates the binding energy. Assume whatever you want for the escape fraction, and you can try and see which kind of star-forming systems will be the key sources of reionization. Yes?
So before you mentioned, when you were talking about the escape fraction, that when you're talking about more evolved stellar populations, only then can you expect certain lines of sight to form which are letting the photons escape through supernova feedback. But now when you mentioned that supernova feedback would also quench the star formation, so does the age of the stellar population in the galaxy also counter into like which is contributing more? Like young stellar populations are contributing more because of...
You know, so in general, we are always talking about young stellar populations because old stars don't produce too many ionizing photons. They're all gone within a few tens of million years. So you need young star formation. But the point is just so, imagine a supernova explodes after 3 million years. So something which is like, let's say 100 solar masses, a star will explode after 3 million years. Now it's a game of, I have the next, let's say 15 million years to keep producing ionizing photons. In the next 15 years or in the next 12 million years, can this supernova clear channels or not? Sorry, does it make sense? The next generation of star formation, but not those stars which are already forming within the same molecular cloud. Yeah. Okay, so just to show you how these things actually evolve, what I'm showing you here is the fraction of reionizing photons that are coming from galaxies as a function of the halo mass. This is for 3 different redshifts. Let's just look at this redshift 10, which is the intermediate line. So if I assume a constant escape fraction, so it's the same for all halos, the star formation efficiency scales with the halo mass. What you're going to find is that low mass systems will provide most reionizing photons. So half of the photons will come from systems which are below 10 to the 9 solar masses in halo mass. But we just decided that the escape fractions are going to scale the younger and the less metal rich, the less dust rich your stellar population. And so if this is true, then you will shift the sources of reionization to even lower mass things. If, on the other hand, the escape fraction scales with halo mass, so larger things can have more ionizing photons escaping, then you will shift the sources of reionization to higher mass halos. So as of now, the situation is that if you think of this really, really simple scenario where you are basically just working with supernova feedback, constant escape fractions, low mass sources will provide most of the reionization photons. And I'm just going to show you in a few minutes how this will evolve as you make the situation more and more complicated. So this was star-forming galaxies, right? But we said, well, we also have accreting black holes in the early universe. So what about the second population? So the James Webb has been incredible in yielding black holes out to extremely high redshifts. I think maybe Roberto will give you a lecture on this. Maybe, okay. Okay, but anyway, let me just show you what is happening. So here, what I'm showing you is the black hole masses that we are measuring as a function of redshift. All of these points that you see here, so there's 32 points here, and these are all black holes that are spectroscopically confirmed by the James Webb. So this is very outdated because this is a paper from last year, and then we have like just so many new systems. So, okay. Well, okay, against this slightly outdated scenario, what I would like for you guys to notice is that we are detecting lowish mass black holes, so between 10 to the 6, 10 to the 8-ish, which are at redshifts below 7. So these are things we already expected from surveys with, for example, the Sloan. So this is not an extraordinary population. What is extraordinary is that at redshifts of about 10, if you apply local calibrators, we're inferring black holes which are as massive as 10 to the 8 solar masses. Now, such large black hole masses are very, very hard to form in the early universe. And I think Marta is going to explain to you everything about black hole, supermassive black hole growth, Eddington rates, etc. What I will just would like for you to look at is that theoretically we have a problem in how to seed and grow these black holes. So the metal-free stars, which Andrea taught you about, they give you seeds which are of the order of 100-ish solar masses. Let me assume that these black holes are seeded by metal-free stars. If I allow them to, if these seeds to form at a redshift of, let's say, 25, I allow them to accrete at the maximum Eddington rate, which Martha will teach you. you are able to explain these black holes, which are at redshifts below 7. So this is how the black hole mass would grow as a function of redshift. But to explain these extremely massive things, you need to start with seeds which are at least 10 to the 4, 10 to the 5 solar masses at a redshift of 25. So suddenly, we are in this regime where we are requiring extremely, extremely massive seeds to have formed very early on in the history of the universe. There are multiple ways of doing this, but none of them are trivial, and so it's not clear why we should be seeing such big outliers with these tiny volumes that we are probing with the James Webb. And for all those of you who are going to be around to look at LISA, LISA is a detector which is aiming to look at gravitational waves from mergers of massive black holes in the early universe. So just to put this in context, as a function of redshift, what I'm showing you is the black hole mass. All of these dots that you see are all of the black hole masses that we had pre-James Webb. LISA is going to detect black hole mergers of black holes between 10 to the 4, 10 to the 7 solar masses at redshifts above 2-ish. So far, we have invoked many different ways of forming these black holes. So low mass black holes from these metal-free stars were okay to explain lowish mass black holes in the local universe. We needed more massive seeds from either some kind of nucleation or from some kind of direct collapse to explain already these high redshift quasars we were seeing from the Sloan. And now, if you look at the black holes we're detecting with James Webb, they are here. This is a completely new part of the parameter space in terms of the black hole masses as a function of redshift, and we've just never seen things that are so massive so early on in the history of the universe. And so this requires really new ways of forming and growing their seeds. I'm not going to discuss this in detail. If you're interested, please come have a chat with me. But what I want to show you is what is the correlation between these black holes and the galaxy population that we're actually detecting from all of these, not just from the James Webb, but putting together all of the data that we have so far. So here, I'm showing you again the UV luminosity function, so number density of galaxies per co-moving volume as a function of the UV magnitude. This is at a redshift of 5, 7, and 10. Now, I want you to look at all of these so you can kind of barely make them out. The reddish points that you see are all pure star-forming galaxies. The bluish points that you see are the UV luminosity function estimates that we have from the James Webb. All of these grayish points that you see are the UV luminosity function from AGN that we had from ground-based observations. So ground-based observations told us we had black holes in really massive systems. But now we are beginning to find an increasing number of black holes in what were traditionally thought to be pure star-forming galaxies. There is an issue here that when you look at the UV in these systems, it's probably coming both from stars plus black hole, and it's very hard to break apart what fraction comes purely from the black hole versus what fraction comes from the stellar population. Nonetheless, same situation persists at redshift 7, where you have a huge number of black hole hosts in really low mass galaxies. So these are things which are 10 to the 9-ish solar masses in terms of halo mass. And these were traditionally just supposed to host pure star formation. So now we are suddenly in a situation where if I again plot the halo mass function, so number of galaxies per co-moving volume as a function of halo mass. For these low mass things, we used to think this was powered by star formation. This end was supposed to be star formation plus black hole accretion. But now what's happening is we are finding a huge amount of black hole accretion in this low mass part of the parameter space. So this is of the order of 10 to the 9-ish or so. So suddenly, so we were just discussing this, right? Too many ionizing photons from pure star-forming galaxies. And now here is a second component, which is black holes, which are much more numerous than we had expected. And the key problem is they are also contributing, it seems, a lot to the low luminosity end or the low mass end of the halo mass function. So this is a second overproduction crisis. So I'm going to end this part very quickly by showing you, let's make some simple assumptions. Let me use the results of this low redshift Lyman continuum survey where we said that the escape fraction correlates with the beta slope. So the younger metal poor, dust poor a stellar population is, larger is the escape fraction. Escape fraction as a function of mass. And these are values for 3 different redshifts. You don't have to care. You can just look at the blue line. So for low mass systems, you find escape fractions which are of the order of 20%. Because things do have some amount of dust. No galaxy we are finding is completely dust-free, completely metal-free. So escape fractions are of the order of 20%. They decrease as you probe more and more massive systems because they have older stellar populations, more dust, more metals. Now for black holes, the escape fraction is a completely open problem. We have no idea what this correlates with. So let me make a super simple assumption. I say if I'm a black hole and I have an accretion disk to accrete from, this accretion disk probably has a combination of dust, metals, and gas. The more the accretion rate basically depends on how massive my accretion disk is. So the larger the mass in the accretion disk, the more I can accrete. But this also means if I accrete a lot, I produce a lot of ionizing photons. The moment they leave the black hole, they're going to see a huge amount of luminosity. So you can make a really simple assumption where you say that the Eddington fraction or how much a black hole can accrete is directly proportional to how much optical depth it's going to see. So let me make this assumption. Low mass black holes don't really accrete too much. They are in systems where they just don't have too much gas and dust to accrete. So the escape fractions can be as high as 100% because these black holes are sitting there. There's no accretion disk. It was maybe blown away either by supernovae or by black hole feedback itself. As you come to higher and higher mass black holes, they are able to grow accretion disks around themselves. Escape fraction drops to about a few percent. So now what if I put this all together? If you put this all together, you will end up in a situation where you are looking at the number density of ionizing photons, which are escaping out of galaxies now as a function of redshift. The black line that you see is from star formation plus black holes. And now this is calibrated to all of the observables I have shown you so far for star-forming galaxies and for black holes. So you can ask, well, what is dominating this escaping rate of ionizing photons? So let me show you the contribution from star-forming galaxies. It's this red line. So you can see for most of reionization history, it's actually star-forming galaxies which are dominating the ionizing photons that are escaping to contribute to reionization. And most of these, which is the super thin reddish line that you can see, most of these are actually coming from star-forming galaxies which are in stellar masses below 10 to the 9 solar masses. So low mass star-forming galaxies seem to be providing the bulk of reionizing photons. Although we have a lot of black holes, they are emerging, so that is the blue line, they are emerging really late. They kind of, if you account for the escape fraction, they are becoming important only by a redshift of about 6 or so when reionization is more or less complete. So they are super important at the end stages of reionization, but they are not driving most of the process of reionization. Now you could say, well, okay, you just said we don't know what the escape fraction of black holes is, right? Maybe it's 1. I mean, what do we know? That is this dotted blue line, which you guys can barely make out. In that case, if I allow an escape fraction of 1 for black holes, they can overtake the galaxy contribution as early as a redshift of 7.5-ish. So they would change the reionization history. But then again, you would be in a situation where you would suddenly have too many ionizing photons. This means, again, you would overshoot or overpredict the optical depth for reionization, and you would reionize the universe too early. So if you demand that you match all of the reionization observables we have so far, the picture that seems to be emerging is that low-mass star-forming galaxies are driving the process of reionization. Black holes have some impact, and this is mostly in driving the patchiness of reionization in its end stages. But please do not think this is the complete picture. There's a lot of unknowns, as you guys have probably seen from this. I'm going to show you more caveats. And so there's a huge amount of discussion in our community as to the role of black holes versus star formation. And so there's a lot of references here where people are really showing that black holes alone could even reionize the universe. You can adjust parameters in different ways so that you still match all of the reionization observables, perhaps not galaxy observables. But yeah, like black holes alone could reionize the universe. This is not something that has been ruled out. So I would encourage all of you to really keep an open mind in terms of the sources and the history of reionization. Okay, so I'm going to end this part of the lecture, which has run like super over, with this last thing, which is, so far we discussed metal-enriched star formation, so what we would call POP2 star formation, and we discussed the role of black holes. But what about the role of these metal-free stars, which Andrea was telling you about? So these must have been the first generations of stars which formed. So why don't we really care about POP3 stars when we're talking about the reionization of the universe? So this is results from a review by Klesson and Grover, where they are looking at all of these different models for forming POP3 stars. And they are basically trying to look at the star formation rate density, so star formation rate per Coulomb moving volume as a function of redshift for metal-free star formation and metal-enriched star formation. I don't want you to look at any of these individual lines. They're like all over the place. But basically, by a redshift of 15, this is the upper limit of POP3 contribution to the star formation rate density. So what you're finding is that POP3 stars actually start driving the star formation rate density of the universe. But by a redshift of 15-ish or so, really depending on how you form these first stars or what you think their number densities are, their number densities are becoming really subdominant to metal-enriched star formation. So POP3 stars can actually start the process of reionization, or they do start the process of reionization. But then there is a transition where metal-enriched star formation is basically going to take over. But as we were discussing on the lecture of the first stars, the IMF of the first stars is really poorly known. And we just discussed the flatter the IMF, the larger is the production rate of ionizing photons per unit UV. And so how many ionizing photons can these things actually produce? What is the evolution of their star formation rate density? Another problem is for the same number of baryons turned into stars, POP3 stars can produce 100 times more ionizing photons compared to POP2 star formation. So even though there are fewer, they are much more energetic in terms of producing ionizing radiation. This is an unsolved problem, and so I would just leave you with this question that you can ponder about. So in which situation would POP3 stars actually start dominating the reionization budget? And in that situation, would you still be able to match your reionization constraints? And so this is an open problem I will leave you with that you can think about. And I will now move finally to lecture 2. Yeah, I mean, we're like super behind time. This is not going well. Okay, so sorry guys, can I ask, are there any questions before we kind of jump more towards the large scale physics? Yes.
Regarding this slide,
Yeah.
for population to start, it's more a matter of stellar poverty, so the mass ionizing power of population to start, or it's more a matter of the more top-heavy events of population to start. This fact that, of course, they produce higher flux of ionizing photons.
You know, but that is independent of the IMF. What you're saying is for the same amount of, no, okay, so what I would say is it's a combination. It's how many ionizing photons you produce, how many are going to escape out of these different kinds of populations. It really depends on what's happening in the halo in which they are sitting and how many of them you have.
But the main effect is more likely due to the stellar property of producing more ionizing photons, or the fact that the IMF is more top-heavy. They're both an effect of metallicity, I guess, but which has the
Sorry, what do you mean? Like from the IMF, like how many do you produce versus what?
like if we have to say the same IMF for a population 3
Yeah.
and a population 2 cluster of stars,
Yeah.
of course we have the population 3 stars cluster and have a higher ionizing power.
Yeah.
But if we change the IMF and we switch to a top-heavy one,
Oh, sorry. So this factor 100 was for a top-heavy IMF for POP3 stars. Yeah, but it doesn't, yes, I mean, it's all mixed together, you know, like, so for every stellar population, for every IMF, you have to calculate how many of, what is the relative number of POP3 versus POP2 stars in a given halo.
Sorry, but I think
Yes.
if I may,
Yeah, sure, of course.
the question I think is on the number of photons that you create per barrier into stars.
Yes.
And so in POP3 stars, you have 100, there's something like 10 to the 5 photons per barrier.
Baryon into stars, yes.
Usually it's 3,000 or 4,000.
I think it's 4,000, yes, yes.
So it's 25 more ionizing photons per barrier.
Baryon, which is converted into stars, yes.
Independent on the IMF, just the method of stars.
Sure, but if you then scale up the IMF, you get an even higher number. Do you know, like, exactly, yes, yes.
yeah, if we consider like a top-heavy IMF
Sure.
for POP2 stars and a normal IMF for population 3 stars,
Sure, you can, yeah, so I can kind of see what you're getting at, like what would you have to do to the IMF of POP2 stars to have the same number of photons out, right? So I think if you make a POP2 IMF completely flat, you can get 30,000 ionizing photons per baryon, which is turned into stars. I think it changes by a factor 10. So, you know, like, and then if you assume for POP3 stars, it's saltpeter, for example, you would decrease it, I think, by a factor 5-ish. So POP3 stars would still win in some sense, but not by a factor 100, but maybe by a factor 5. You know, but I think, yes, like you can play around with the IMF, sure, yes. Yeah. Sorry, does this make sense? Yeah, good. Okay, so with this, I would very quickly like to give you a global view. So far we have discussed about what is the global process of reionization, what are the key sources, what are the indicators that this process actually happened, and we have some sort of a handle on the end stages of reionization. We have some sort of a handle on the reionization history. And so far, we are kind of converging on star-forming galaxies and AGN being the key drivers of the reionization process. So the relative fractions will depend on what you think is happening to star formation or AGN accretion as a function of the halo mass or as a function of time. So now let me show you guys a little bit more about how exactly does the process of reionization take place. So how exactly do these ionizing fronts propagate from galaxies into the intergalactic medium? Very briefly, we're going to touch upon the temperature evolution of the IGM during the epoch of reionization. And something that is extremely crucial, and I think maybe Yoki will tell you more about this. I don't know, maybe you will. Is the feedback from reionization on early galaxy formation, because Sphinx is a very, very good simulation for testing this. Okay, so let's discuss about the propagation of ionizing fronts into the IGM. And I think you guys will realize that this is a very similar equation to what we solved to calculate the volume filling fraction of ionized regions. So what we are basically saying is that the expansion of this ionized region depends on how many ionizing photons you are producing, multiplied by how many of them are able to escape out of the environment. How many recombinations do you have? So let's say I'm a source, I'm producing ionizing photons, but the gas in the ISM is so dense, it keeps recombining on extremely short time scales. I can keep producing as many ionizing photons as I like. Most of them will be absorbed by these dense Lyman limit systems within my vicinity. And so this ionized region is not going to grow very large. We also have to look at the expansion of the universe, but we can ignore that for now. And so for the expansion of these ionizing fronts into the IGM, the most crucial quantities, again, are the escaping fraction of ionizing photons, and now the clumping factor of the intergalactic medium nearby these sources. So this is your, again, your source term. This is, again, your recombination term. So this is really reminiscent of this propagation of reionization on a global scale. So here, now the problem is, let me reiterate something which we are going to now start discussing, which is this clumping factor of the universe. So the clumping factor of the IGM is really, really poorly known. So the universe, I think, as you all know, is not homogeneous. So here, for example, is a simulation of the formation of the cosmic web. Each of these dots that you see, or these shiny things that you see, are basically halos. They are arranged in your cosmic web. If you assume baryons track dark matter, at least on large scales, then this is where most of your gas will be concentrated. And in these low density regions, which are your voids, you would have a lesser gas fraction, you would have less gas masses. So now what you guys can already really anticipate is that if I'm a source sitting here, I produce ionizing photons, they will preferentially extend into regions which are low in density. If on the other side I have a region which is very high density, the ionizing photons will propagate to this region, but they will not really, the ionization front will not be able to expand because you will have too many recombinations, which will stop the progress of this reionization front. So this is a very nice simulation from a review by Nedin and Maddow, where they are basically showing you the ionization front, which is this reddish colored region, as a function of the local density compared to the critical density of the universe. And what they are showing you is where you have regions of very high density, this gas is not ionized because you ionized it, but then it's recombining on a very short time scale. However, if you have low density regions, the ionization fronts can very easily propagate into those low density regions. High density regions will stop the propagation of ionization fronts because you have dense gas, and so it keeps absorbing all of these photons you are producing. So what I want for you guys to just remember from this is that ionization fronts are not spherical. So everything we have been doing so far was in this spherical symmetry where we say ionizing source produces a spherical Strömgren sphere of ionization around itself, but this is not what is happening in reality. These ionization regions are really, really weird in terms of their shapes, really dependent on the local density around the source. So why do we care? Because if you remember, we said that the recombination time depends on the density of hydrogen as a function of redshift times this clumping factor, where the clumping factor is basically just telling you how overdense the gas is in a given patch of the universe compared to the critical density. So this is the simplest way of thinking about this. So if this is the critical density of the universe, the floor here, if I have a higher density, then I say the gas is clumped. The more clumped the gas is means the higher in density it is. So for a given production rate of ionizing photons, so let me have an X number of ionizing photons that are produced by all of the sources I have. We want to look at the propagation of the ionized fractions, of what fraction of the universe is ionized. So it's the same equation we have seen before as a function of redshift. And now I want you to look at the volume filling fraction of these ionized regions for different clumping factors. Clumping factor is 0, but it's not really 0, so then this would be 1. So if you are sitting at the critical density of the universe, let's say you can fill all of the available volume by a redshift 20. So this is just an example. It doesn't really matter. You don't have to look at the exact redshifts. Imagine that the clumping factor is as high as a factor 30. What this is going to do is you start reionizing the universe, it recombines. You again reionize that patch of the universe, it recombines, and you have to keep reionizing it multiple times depending on how fast it can actually recombine. So for the same production rate of ionizing photons, if you increase the clumping factor, instead of finishing now at a redshift of around 20, reionization is going to drag on until a redshift of 10. So the clumping factor is incredibly important in modeling and trying to really figure out the history and the topology of reionization. So you will say, okay, but why is it so, so why has it been so hard to figure out? So this we are going to do in a second. I also want to raise another issue with you, which is somehow related to this, which is that the temperature of the universe evolves because of reionization. So here, let me show you a spectrum. So this is just the flux as a function of the rest frame wavelength. This is one of the spectra from this low redshift Lyman continuum survey. So you can really see the emission of ionizing radiation. So for example, the yellowish line that you see are for a specific source. The black line is just the average over all of the sources that are leaking Lyman continuum photons. What I want you to look at is the fact that above 916 angstrom, so all of these photons below 916 angstrom are going to ionize hydrogen, right? You can see you have a continuum of photons extending down to 860. So these are much more energetic than the 13.6 electron volts you need to ionize hydrogen. So these guys can ionize hydrogen. Sure, all of them can. But what else are these extremely highly energetic photons going to do in addition to ionizing hydrogen? Very good. So they heat up the gas. Because 13.6 electron volts goes into ionizing hydrogen, the rest is dumped as heat in the gas in the intergalactic medium. So now remember that we said that the temperature of the CMB is basically 2.73 times 1 plus z. So at a redshift of 9, for example, the CMB temperature is 27 Kelvin. But when you dump this energy into the IGM, this can raise the IGM temperature up to 20,000 or even 50,000 Kelvin, depending on whether it's what kind of star formation is it. So is it pop 3, pop 2? And if you have AGMs, they can raise the temperature to 10 to the 5 Kelvin. Now, this is problematic, right? Because reionization is happening all over the universe. This is not a local process. So what we are starting with is we start with a universe which is sitting at the CMB temperature. As reionization proceeds, first the temperature rises in ionized regions. But by the end of reionization, we said you have a continuous background of reionization, which means you also have a continuous temperature background. So by the end of reionization, by a redshift of 5-ish or so, the temperature, instead of being 18-ish Kelvin, is now going to be of the order of 20,000 or 50,000 Kelvin. So the universe heats up by more than 4 orders of magnitude in temperature purely because of the process of reionization. So here is a very nice simulation from Yoki. So this is the Sphinx, where they are trying to show you the evolution of the temperature at different redshifts. So these are very highly resolved simulations. We're not going to go into the details, but if you're interested, please ask me or Yoki about this later. So here are the temperatures at a redshift of 10, 8, and 6. And in regions very close to galaxies, the temperatures are of the order of 10 to the 5, 10 to the 6 Kelvin. But in these ionized regions, the temperatures are as high as 10 to the 4, 10 to the 4.5 Kelvin. And so this is something that is clearly emerging out of all of the models. I mean, you don't even need a model for this, actually. But the process of reionization is really, really going to heat up the universe. So now, let me raise a question. I have this gas, which is sitting in the intergalactic medium. And let's say some of this gas is really dense, so it's clumped. What is this temperature going to do to this clumped gas? very good. So actually, this is one thing that has been super, super complicated. It has emerged over a lot of research that the clumping factor by itself has been extremely hard to calculate because it really depends on what are the sources of ionization, what is the temperature evolution of ionization. But the process of feedback itself, of reionization itself, has a feedback on this clumping factor. So here is a really old model from 2007, where Ilya et al. Were running these simulations where they put in sources and they were saying, okay, let's expand these ionization fronts. Let's even calculate temperatures. You can do that. They were inferring a clumping factor which was evolving very, very mildly with redshift. So it was not evolving super much. But because they were not accounting for this pressure which is exerted by warm gas on these clumped regions. So this was something that has emerged from a number of models. I'm just showing you one here from Pollock et al. As early as 2009, where they said that if you actually account for the fact that this temperature is going to heat up or exert a pressure support on even dense gas, the clumping factor actually evolves extremely differently. And now may I remind you, this is one of the key bottlenecks for reionization because this is our recombination term. And so this is one of the key problems that you require an information on clumping factors to figure out the process of reionization. But reionization itself has a feedback effect on this term. So now it becomes an intermixed problem where you have to simultaneously track the process of reionization and its feedback effects. And it's going to get worse, but before that we have a question. Yes?
Sorry, I think I lost like physical intuition of what the clump factor represents. You had an equation that represented like the expectation values of your H2 region or your number density of H2 regions.
Yep.
But like physically a C of 30 versus a C of 1 or 0.
What does it mean? Oh, I see. Like you can also just think of this as the density above the critical density. So this is 30 times the critical density.
So just higher means like significantly more dense patch.
Yes, yes, exactly, yes. At the simplest level, this is basically how you can think of a clumping factor. It's just telling you how overdense a patch of the sky is compared to the critical density of the universe. Yeah. Okay, so now we are really in the regime of reionization feedback. So again, let me just show you what is happening. So this is a schematic of reionization. All of these gray patches that you see are ionized regions. All of the bluish color that you see are neutral regions. So in the neutral regions, the temperature of the IGM is the ambient CMB temperature, which is evolving as roughly 3 Kelvin times 1 plus redshift. But in these ionized regions, the temperature is going up to about 20,000 or 50,000 Kelvin, depending really on the sources which are driving the process. So now let me anticipate a situation. So we have an ionized region which is created by a galaxy. In this ionized region, the temperature is really high, 20,000, 50,000 Kelvin. So let me say there's a low mass galaxy which is forming in my ionized region, because we know galaxies are clumped. We know things form in proximities. So this little galaxy is hit by this reionization background. It's called an ultraviolet heating background. It gets hit by this reionization background. So what should this little galaxy do? What happens to its gas mass? Sorry? I'm hearing like answers. Shout them out. Okay, so one thing is this: if I'm this little galaxy, I'm hit by a background. Everything around me is really warm. So one idea is that if I'm trying to accrete gas, either I will exert an external pressure support so I don't accrete that gas anymore, or I accrete the gas, but it's accreted really, really hot. So now this gas is heated to 20,000 Kelvin, somehow has to cool to a few tens of Kelvin to form stars. So this can quench star formation. What else?
Expel gas from the galaxy.
Sorry?
Expel gas from the galaxy as well.
What do you mean expel?
Like lead to more gas outflows.
Okay, yes, almost. Okay, okay,
So it's mostly the same.
yeah. Thank you. Yes, very good. So here is the virial temperature of a halo. I mean, it basically just depends on the halo mass to the power 2/3, slight dependence on redshift. Basically, at redshift 9, a halo of mass 10 to the 8 solar masses has a virial temperature of 20,000 Kelvin. So now imagine my binding energy is the same as the energy of this background I am irradiated by. The gas gets photoevaporated. So this gas can even leave the halo. It can go sit in my circumgalactic medium, or it can even go into the intergalactic medium. This remains extremely highly debated. But the fact of the matter is that once you start the process of reionization, this is going to have a feedback effect on low mass sources that are forming in the early universe. But now we're in a slight problem, right? Because we decided these low mass halos are the key drivers of reionization. So I'm at redshift 15. I start reionizing the universe. Then these little things at a redshift of 9 are suppressed. Then I reionize. But what is now driving the process of reionization? As reionization proceeds, I'm going to suppress more and more of those tiny things that are supposed to drive the process. So this is another fundamental problem in modeling the process of reionization. How is this very process killing off the sources that are responsible for driving it, and how is it affecting the clumping factor, which really limits the progress of ionization fronts? So there's a huge amount of debate in the community, but what I want for you guys to remember is we don't have consensus. We don't have any consensus on what exactly is the impact of this reionization background on the gas contents or star formation efficiencies of galaxies. And the reason is the following. Let's say I'm a low mass galaxy. By the time I'm hit by a reionization background, I'm basically able to cool all of my gas. So the gas is so deep inside the potential well, it really doesn't care about this reionization background. In that situation, I don't really care whether I'm hit by this background or not. Imagine another situation. I'm a low mass star forming galaxies. I formed my stars, and I got rid of the rest of my gas because of supernova feedback. I don't care about this reionization background. I'm not forming stars anyway. So there's a lot of these sorts of arguments which are happening in the community that the impact of reionization feedback really depends on when any halo is hit by the reionization background, what is the strength of and the temperature of the reionization background, and where is the gas, or how cold is the gas in these halos when it's hit by this background. And so here are the three different possibilities. There is no impact of reionization feedback on galaxy formation. Gas is too deep in the potential wells, or it's already ejected, so who cares? There is a gang which works at the level of maximum impact. So if reionization happens, all halos below a certain mass, which corresponds to the virial temperature, which equals to the temperature of, sorry, let me say this properly. So if you calculate the virial temperature, equate it to the heating temperature of this reionized gas, all halos which are at lower virial temperatures are completely and utterly suppressed. So this is the worst effect that you can have from reionization feedback. Almost nobody believes that this should happen. But the most reasonable scenario is what is called a partial impact, that low mass galaxies which are sitting in ionized regions are the only ones which feel an effect of reionization feedback. Again, depending on when they are hit by the background, where their gas is, et cetera, et cetera. So I'm just going to show you one example of what can happen to the gas masses as a function of halo mass at a redshift of 10, 8, and 6. But you can just look at the top lines and this bottom line. So at a redshift of 10, the universe is only a few percent ionized. So there's not too many galaxies, low mass galaxies, which are going to sit in ionized regions. So if you look at the gas contents of halos in ionized regions or neutral regions, I mean, it looks very similar. And it's just because not enough of the volume of the universe has been reionized. But by the time you're at a redshift of 6, The dotted line is if you had no reionization feedback. The solid line is if you have reionization feedback. So here you can see by a redshift of 6, reionization is 90-ish% complete. So 90% of the volume of the universe is covered by ionized region. So if galaxies are homogeneously distributed, roughly 90% of them would be affected by reionization. What you're finding is that for things which are less massive than 10 to the 9-ish solar masses, you're basically able to suppress all of their gas mass, which means you're able to suppress all of their star-forming capabilities. So now, the situation is the following. We said these things can form stars, but suddenly we're saying, hey, wait a minute, these things have no gas mass left to form stars. And so this is, just to give you an idea, this is some of the key complexities we are facing, that reionization is a process which has a huge, or can have a huge feedback on the very sources that are responsible for driving this. And so to again put this into context, let's go again back to this very simple plot which we were discussing. So where are most of the ionizing photons coming from? So this is a fraction of ionizing photons as a function now of the halo mass. So you guys all remember we said in this really basic scenario where you scale the star formation efficiency with the halo mass, constant escape fractions, we said 50% of ionizing photons come from things which are below 10 to the 9-ish solar masses in terms of halo mass. Now, what if all of these low mass things are suppressed by reionization? So I'm just trying to do a maximal or minimal estimate to see how much can reionization actually change its own sources. So let me suppress the star formation in all halos below 10 to the 9-ish solar masses. Suddenly, what you find is all of this stuff which is below 10 to the 9 is not going to provide any ionizing photons because it has no star formation, it has no gas. And so the sources of reionization, purely by including the effect of UV feedback, I'm not doing anything else, this is the only physics I'm changing, the sources shift to much, much higher masses. And so this is why when we were discussing which are the key sources of reionization, a lot of you were convinced it was low-mass star-forming galaxies. But the problem is if reionization can suppress a significant fraction of those low-mass star-forming galaxies, they're not going to form stars. And so the sources of reionization are going to shift more to your intermediate mass halos, where the virial temperatures are high enough that they can hold on to their gas content even when reionization takes place. So I think we have like 10 minutes, so I don't want to do like all of the computational challenges, but just to give you an idea of.
You can take 10, 15.
No, but I mean, it's like, it's poor kids, I mean, you know, like, I would die learning about reionization. No, okay, so, you know, like so far, I've highlighted a lot of these problems we are having in trying to model reionization. So now many of you could say, well, why don't you just model it from first principles? You know, take a simulation, reionize the universe, look at the effect of feedback, look at the effect on the clumping factor, and, you know, precisely what is the problem in trying to solve this from first principles. And the problem is really computational. So remember, reionization is a large-scale process. This is a cosmological process happening on the scale of the entire universe. So if you do want reionization on a representative scale, you should model a volume which is about 200 megaparsec whole cube. So 200 megaparsec is the side of the box that you want to model to converge on the large-scale topology of reionization, or the large-scale distributions of ionized regions. So this is something that has emerged out of a lot of different tests for reionization models. However, let me remind you that the galaxies which are producing ionizing photons, those galaxies have sizes of about 100 kiloparsec or even smaller if you go to higher redshifts. And the regions where star formation is actually taking place, where you're producing your ionizing photons, where you are demanding the escape of ionizing photons, this is all happening on the scales of a few tens or a few hundred parsecs. So to simulate reionization, in principle, you have to go over 6 or 7 orders of physical scale. this is, if you remember nothing else, please just remember this is one of the fundamental problems we have just in terms of the physical scales that we have to model. And adding to the complexity of the problem is the fact that all of this star formation, et cetera, we were discussing, all of this is happening on a few million-year timescales. You want star formation, you want your supernova channels for escape, et cetera, et cetera. Everything is happening on a few tens of million-year timescales. But the percolation of bubbles can take place on billions of year timescales. Recombinations can take place on extremely large timescales. And so the range of just physical and temporal scales that you need to model is one of the key bottlenecks for modeling the process of reionization. Guys, can I ask, are there any questions at this point? Yes.
So if this reionization feedback has that much of an effect on star formation, can we probe this feedback by looking at the relation between the halo mass and the age of star population?
Yes, actually this is something which people do in the local universe. So for example, the missing satellites problem, that we should have had more satellites compared to what we see. One of the solutions was maybe these were suppressed because of reionization. So they are really tiny. They are forming in a universe that is heated because of hydrogen reionization. There's also helium reionization, which we will not discuss. But yeah, they are forming in this extremely hot medium. And so because of that, their gas could be either warm or photoevaporated, and so they're just not forming stars. So this is one of the things which people were trying to do. Yes, yeah. I think the problem is at high redshifts, we don't have enough cosmic time to test this. And also you want to go really, really faint or really low mass, and those systems are extremely hard to find. So you don't know if you're not seeing them because they're just too faint or they're really not forming stars. Sorry, does that make sense? Yeah. Yeah, of course. Okay, so in the last 2-ish minutes, let me just try and show you what people have been doing in terms of trying to solve this problem. So given the complexity of the problem, there's a lot of different ways in which you can try to solve specific aspects. So if you're interested, this is a very nice review by Nedin and Maddow, where they tried to summarize all of these different methodologies for reionization. They tried to give you an estimate of how many simulation boxes were run, what were the box sizes, resolutions, et cetera, so that you can really have a good idea of these different ways in which you're trying to address the problem. So I will just show you 2 basic approaches, and immediately you will see why neither is complete. So the first thing you can do is you can say, I care about the large-scale cosmological process of reionization, so let me take a really big box. Let me take a box which is a few hundreds of megaparsecs. So for this, you would start with something which is a dark matter-only simulation. On these scales, you can't follow galaxy formation at parsec scale, so you will use some sort of semi-analytic recipes or whatever you want to do to link some sort of galaxy formation to all of the halos that you have. So it's really your choice what you do. There's numerous ways of doing this. If you're interested, please come talk with me. For each of those sources that you link to your dark matter halos, you can say, well, how many photons do I produce? How many photons emerge out? You can start to build your reionization fields. You can start to look at the large-scale clumping factor of the universe. You can start to look at the large-scale temperature distribution. But something that you cannot do from first principles is look at the galaxy properties in any of those halos, because you just don't have the resolution. So if you look at these kinds of boxes, it's really highly resolved, but you still don't have the resolution to look at individual galaxies. So this is really good to get a global, large-scale view of what is happening with reionization. And so these techniques are called semi-numerical, because it's not completely numerical, it's just semi-numerical. On the other end, we have techniques which are called fully coupled. So there's very nice simulations which are CODA, CROG, Sphinx, or even Tizan. You can see that the box sizes are now not as big. So these are generally a few tens of megaparsecs, extremely highly resolved. So you can see you can resolve things down to a few tens of parsecs in many of these situations. And so here is an example of the cosmic dawn simulations, where they are really coupling galaxy formation and reionization, but it's on small scale. So you don't converge on the global topology or global history of reionization. But then you can start to look at things like how many ionizing photons escape, because you have the resolution to look at the escape from galactic environments. You can look at how these ionized bubbles are percolating, the temperature distribution, and the evolution of the gas density. So these simulations are fantastic if you want to look more at the effect of reionization on the sources as compared to the large-scale topology of the process. And the results are, in some sense, very similar. So here are results from the CODA simulations, where I just want you to have a look at how much of the star formation you can actually suppress in these fully coupled simulations. So this is the star formation rate as a function of the redshift for different halo masses. This is if you include reionization feedback. The right panel is exactly the same if you don't include reionization feedback. And I think even by eye, you can figure out for high mass halos, reionization feedback has almost no effect. So for halos above 10 to the 10 solar masses, reionization is basically irrelevant. However, when you are looking at low mass halos, so below 10 to the 9.5-ish solar masses, you can completely suppress star formation in low mass halos by the time reionization is complete. And so this is the result from one simulation. Seems to indicate reionization is super, super important, especially in determining the properties of low mass things in the early universe. But again, I would urge a lot of caution, because as we have been discussing, all of this feedback really depends on how strong your ionization fields are, how fast they propagate, when they hit this halo, how much gas it has, and how much gas they can actually photoevaporate. Okay, in the interest of time, I will not talk to you about 21 centimeter. I think Salim is going to tell you everything about looking for 21 centimeter. But if you're interested in this relation between 21 centimeter and galaxies, please come talk with me. So I think I would just like to end with this brief recap that I hope I've convinced you that reionization has really been a hard problem to solve from first principles. And it's mostly because of the huge range of temporal and physical scales that are involved in this process. The progress of reionization, of course, depends on what you think are the key sources, what you think is the clumping factor of the universe, how it evolves. But then the problem is reionization can have a huge impact on both of these. It can have a feedback effect both on the star formation in these low mass systems that are supposed to drive the process. Can also have an effect on this clumping factor, which is supposed to limit the propagation of ionization fronts. And so the impact of this reionization background remains extremely, extremely debated. And I think, yeah, like if you're interested in directly probing the epoch of reionization, 21 centimeter is a very powerful probe. But yes, Salim will teach you everything about this, and he will tell you how the 21 centimeter arises. But yes, I mean, I would just like to leave you with hopefully this global picture of reionization and some of the key challenges. So yeah, thank you very much.
You spoke about how reionization feedback could affect low mass forming galaxies. Yeah. But now if we come back to the question of aging contribution and how they are affected by this feedback, particularly, can we expect, because even they are, the accretion rate would be affected with this ionization feedback for driving out the gas. Can we expect the contribution to change, like the amount of contribution by AGNs versus star-forming galaxies due to this reionization feedback?
It's a very good question. I think it depends on on the time evolution of AGN versus star formation. So I think the difference is, like, if you remember, we were trying to look at this. So maybe if I go back to this. So I would point you to this. So for example, star formation is starting really, really early. But at these early times, you don't have enough black holes that are able to do much. So you have really tiny black holes, but they are not accreting at super high rates, which now Martha is looking at me. I don't know. I mean, I don't know what they are accreting at. But in general, they are becoming important at later times compared to star formation. So it really depends on how much star formation you can quench versus how much you can affect the assembly or accretion rates of these black holes. So yeah, I mean, you know, like it's up to you. I think there's different ways of doing this. So you can reduce the contribution from star-forming galaxies, leaving the contribution from black holes more or less unchanged. You know, because you can argue that the gas around a black hole is so deep in the potential well, maybe it doesn't even care about the UV background. Versus this halo is hit by the background when the accretion disk is trying to form, in which case you could completely disrupt it. Sorry, do you see what I mean?
Yeah.
Yeah, so I don't think there's a specific answer that I can give you, but we can discuss more. Yeah, yeah, of course.
I think you and the rest, sir?
Yeah, I had a very similar question, but I'll just add, I guess, just for clarification, the curves in this figure, are these from simulations and they're matching with predictions, or do the simulations that are trying to do everything self-consistently agree with this picture? Is there differences that you painted with this figure?
Oh, sorry, yes, I should have said. So this is just a semi-analytic model in which you're trying to see how things are assembling through time. So this is not a simulation, this is purely analytic. Yep.
And then,
Yep.
so do the simulations agree with this, like, what this finding, like, based off of observations and semi-analytic models, do the first principle simulations agree with this view, or of like how the star-forming galaxies and black holes interplay?
I'm looking at Yoki and I would say no.
Oh, yeah.
Well, okay, so the best simulations resolving small-scale structures, star formation, et cetera, et cetera. I think one of the key problems is, as I was showing you, we're finding an overabundance of star formation with the James Webb. And nobody was expecting this. And so I think people are now trying to tune the simulations to get enough star formation to happen. But remember, most of these simulations are really small volumes. So they can have black holes, but they're not going to have these big black holes, which we're detecting with the James Webb. I mean, they just can't form them. So this is why the field has kind of shifted a little bit. So we're doing more analytics, because we just don't know what physics to put into our simulations to make them match to the observations. Sorry, does that kind of make sense?
Yeah, I think so.
And I think Yoki can maybe add more.
I'll talk a bit about
Yeah.
trying to draw black holes, but that seems to be very, very hard. And actually, the higher resolution you have, the harder it becomes. The challenge for simulation.
Yeah, and this is why everybody's mostly doing things analytically, which is fantastic. Like,
Speaking of feedback, you
Yeah.
talked about supernovae as a source of negative feedback on star formation, but I mean, supernovas produce metals and so on and so forth that enrich the ISM, so can they also be a source of positive feedback? Is that something that's ever taken into account?
I think that's a really good question in the sense of if you have metals, your gas can cool, so the next generation of stars can form with a higher cooling function in some sense. I think the problem is if your supernovae exceed your binding energy, they will get rid of your gas. And so there's just nothing left to form the next generation of stars. And I think another thing is that gas and metals are not two different fluids in a certain sense. So they are mixed to some level. So if you are going to eject a huge amount of gas, you will lose some amount of metals, which is then going to also decrease your cooling rates. Sorry, does that make sense?
Yeah, I think so.
You know, so I think more than supernovae, people were actually also looking at AGN as a source of positive feedback, because when you have AGN feedback, you can induce a lot of turbulence, which could, in principle, enhance star formation in some patches of galaxies. So AGN feedback is the one that I would argue is more positive plus negative. Supernova feedback in general just gets rid of stuff. Yeah. Yes, but we can discuss more later. Yeah.
You've introduced the fact that some low-mass galaxies have been suffering from the feedback of the reionization.
Yeah.
So it might be the progenitor of some population of galaxies that we saw at lower redshift.
Yes.
Do you have any candidate?
Yes. Oh, sorry, all of the satellites of the Milky Way. You know, because this is the stuff we can look at with the highest amount of precision. And I think when the missing satellite problem, so I'm really not an expert, but I will just give you my view on this. So at some point when we were doing surveys around the Milky Way, we were finding too few satellites of the Milky Way. And so one of the arguments was, yeah, maybe these things exist, but the halos are not forming stars because they are forming around the Milky Way, which is the central. And these things were forming around this bigger object. But this bigger object must have been reionizing the universe around itself. So maybe when they were forming, they were immersed in this hot gas, and so they were just unable to cool, form stars. But I think if I understand from local observations, we're finding an increasing number of low-mass satellites, so maybe like this problem is disappearing, but I'm not sure. But yeah, so this is where people were looking for impacts of ionization feedback. Yeah. Yeah. Yeah.
So, I think it's a good time to break, unless there are any announcements. Then let's take Pratika again.
Thank you.